As promised, there are three main hypothesis tests that we're going to go over today with regard to multivariate regression. The first of which is something that you should be very familiar with because we did that in our first module with bivariate regression, and that's a t-test with regard to the coefficient and the standard error of the coefficient. So we're using this for individual regression coefficients to test individual relationships between one covariate and the outcome. And again, we're interested in whether or not there is any relationship. We don't care if it's positive or negative. And so the null hypothesis test that we set up is whether or not beta j, and again, j is just an indicator for any covariate, whether or not that beta is equal to 0, with our alternative being that there is some relationship. The second kind of hypothesis test that we can do is whether or not all the regression coefficients are equal to 0. So in this sense, we're interested in whether or not any of the variables have a relationship. Therefore, the null hypothesis is that any of them are equal to 0. Therefore, if we find evidence to reject the null hypothesis that one or more of them is not 0, then we would have our alternate hypothesis. At least one of these betas is not equal to 0. There is some relationship amongst one of the covariates at least. We can also run a partial f-test, which is just a subset of the regression coefficients and whether or not they equal 0. So in this case, the null hypothesis is that of the coefficients that we're interested in, these equal 0. So among the ones that we're interested in, the alternate would be at least one of these covariates has a relationship with our outcome. And I know this sounds a little bit confusing, so we'll start off with the one that you're more familiar with, which is the t-test. There are a couple ways to think about what we're trying to achieve with regard to a single t-test for an estimated coefficient. And the first is that we're just interested in testing what the partial effect of each predictor is. And in other words, we're testing for the effect of a predictor given all the other variables that are already in our model. The null, therefore, is that there is no relationship. So this indicates that there's no discernible linear relationship under the null. It's important to stress linear relationship here. And again, this is saying that there's no relationship between our variable x and our response variable y after, and I'll pause for a second for you to think about this, controlling for the effects of all the other predictors in the model. So again, this is important because many of these covariates will vary with each other. As before, we have the same setup where if our null is that there is no relationship that exists, our alternate is that at least some relationship exists. So beta should not equal 0. The setup is exactly the same in the sense that we have our estimate of our coefficient over our estimated standard error of the coefficient with a student t-distribution with degrees of freedom n minus the number of covariates minus 1. Why, again, do we use n minus k minus 1? That's because of the number of observations minus the number of variables, but minus 1, and that's because that's the number of statistics that are being used to generate this test statistic. Last, we can then create some sort of confidence interval around our estimated coefficient in the exact same manner, where we reference our t-distribution with the correct degrees of freedom multiplied by our standard error, and that gives us the upper and lower bound of uncertainty around our estimated beta. So as something to consider as we construct the standard errors around, again, our partial effect, so it's a partial regression coefficient, we have to notice that this standard error is going to, one, depend on the estimated standard deviation of our sigma, but also the variability of that given predictor, right? So if we have more variability that we observe in one covariate, then we are inherently going to see a larger standard error around that estimated coefficient. And one of the determining factors of this as well is going to be how much variation this variable is adding given the other variables. So in other words, our coefficient of determination is essentially telling us how much including this predictor after all of the others in our model is adding to the explained variation, which is inherently going to make an impact on the uncertainty that we have around the estimated relationship of that variable and the response. Now, this is also called the variance inflation factor, and this is highly driven by issues that are resulting from multicollinearity. And again, that's just saying that one covariate is highly related to another covariate in the sense that variation in x1 very much explains variation in x2, which causes us to essentially have to generate higher degrees of uncertainty about which relationship is actually driving the true underlying relationship in our outcome. Now, for an example, we can imagine a case where we want to estimate the effects of maybe age, race, gender, and party identification on support for Bush starting the war in Iraq in the early 2000s. So I'm going to go over this in R and briefly just show you how I load the data in. Now you can get this as well. It'll be under labs. The only thing that'll change is the location. Again, this is just pulling in American National Election Survey data. And here I'm in line 5, cutting it down to just the 5 variables that we're interested in. Now, we want to generate our first null hypothesis, so we'll take our first variable, which is an indicator of whether or not the respondent was white or not white. And again, what we're interested in here is whether white individuals have a propensity to favor Bush going into Iraq before the lead up to the war. So let's think, what do we need in order to construct our t-test? We need our estimated coefficient from our regression table. We need to then generate our test statistics, so we need our standard error, and from that we will generate a p-value which we can make an inference from. So the first thing is we need our estimated coefficients and standard errors. I'm not going to go too deep into what's going on with the code. Essentially, I am running the regression by hand. There's nothing to say that you can't go and look at the regression output that R generates and still run a t-test and generate a p-value. But I want you to be confident that you know how to do everything from point A to point B, and I want to provide all the necessary information to do that. So please take a look at this at your own leisure, but there's nothing in here that we didn't discuss last week. Now, from this, we can generate our test statistic by taking our estimated coefficient over our standard error. From that, we have our test statistic, so we'll reference the t-distribution, put in the test statistic, the degrees of freedom, put in lower tail equals false, because again, we're running a two-tailed t-test, and then we'll multiply that by 2, and that'll give us our p-value from which we can make our inference. Now we do this by hand, and it outputs our estimated coefficients, our estimated standard errors, t-value, as well as p-value. So let's take a look at our first covariate, white, and generate some confidence intervals. But before we do that, I just want to show that this works as well just by using LM, and we get the exact same regression results. So again, if we're going to construct confidence intervals for our first estimated coefficient, We just take our t-score multiplied by the standard error, and we can see that the resulting confidence intervals have 0 within them. We can then go ahead and do that for all of our other estimated coefficients. And this is me doing it by hand, but we can also double check our work with R more simply using confint, so confidence intervals. And again, we get the upper and lower bounds. So we can see that the only coefficient that doesn't have 0 within its 95% confidence intervals is party ID, which would indicate that this is the only covariate that does actually have a relationship with our outcome that is statistically distinguishable from 0.